the hardest exam all semester, okay? So please treat it accordingly, and have a couple weeks still to prepare, but please spend time preparing for it. Probably not going to see a whole lot of calculus on this exam. I might give you a function and have you take the derivative like you did on the first exam, a function in 2 dimensions now. And if you look back at the old test, you can see some problems like that, but they're pretty basic. But I don't want to say there's no calculus, because really Calc 3 is all about vectors, or it's a lot about vectors. There's a lot of vector stuff in Calc 3. Now, some of you won't get to Calc 3, right? No, most of you will, right? Chem majors, you take Calc 3, right? Engineering majors, of course, you'll take it too. So it's just we have a couple biology majors, right? Couple biologies. Are you biology? No? What's your major? Your chemistry. Are there no biology majors here? Yeah, so we have a couple biology majors. Y'all never see that. But vectors are a big part of Calc 3, uh, which is largely what we're going into now with the laws of motion. All right. You've probably seen the laws of motion. Our kids, they cover it now in like first grade for Newton's laws of motion. Um, I want to show you a video first. Actually, first, let's just sort of define some basic things. The first grade definition of a force is true for us too. It's just a push or pull on some object. And we'll see two types of forces. We're going to see contact forces. Ever been in a fist fight? Who's been in a fist fight? Nobody? Seriously? Listen. Yeah, all right, thank you, Desiree. Uh, when I was in like 6th or 7th grade, I got in a fist fight with Nelson Zamora because I thought that's what you do, right? Like my brothers, they were always getting in fights. And I thought, well, I need to get in a fist fight. So Nelson Zamora and we got into a fist fight, and when we punched one another, right, that is a contact force, right? Because it requires contact between two surfaces, and it was sort of very typical fist fight, right? We decided we're going to meet after school at that field off campus. We had a fight. We got there. We didn't really know what to do. It was like, okay, should we get started? Let's get started. And then at the end, it's like, okay, well, I guess that's okay. And we shook hands, and then we were friends after that. But anyway, when you punch somebody, that's a contact force. A contact force requires contact between two surfaces. And a lot of our forces uh, are contact forces. Another type of force, listen, we'll have a whole chapter on this in the next semester, are field forces, where we'll define what a field is and talk about some of the different ways that we deal with fields. We'll talk about gravitational fields and electric fields. A field force does not require contact. There are 4 basic types of field forces. We're really only going to deal with 2. The other are sort of subatomic uh, fields. The first is the gravitational field, or the gravitational force rather. This is between objects of mass. We've been sort of tiptoeing around this all along because we've talked about the acceleration due to gravity, and the acceleration due to gravity is due to a force. Anytime you have 2 objects of mass, no matter what their mass is, anytime you have 2 objects of mass, you'll have a gravitational force. So for example, each of you has a certain mass, right? You're all attracted to one another with this gravitational force. It's a small force, but it's certainly measurable. And you can measure the gravitational force between objects of mass in the lab. And there have been some pretty cool classical experiments to measure that force. Small, but measurable to measure the force between you. All right, so you have the gravitational force, gravitational. You also have the electric force, which is going to take up most of our effort next semester. The electric force is between objects of charge. All of these act at a distance. They don't require contact between two surfaces. And then the other 2, just sort of to make the list complete, you have the strong nuclear force and the weak nuclear force. This is in subatomic particles. What holds that nucleus together, right? Because you got a bunch of protons packed in there really tightly. And as you know, objects of similar charge are going to repel from one another. And so if that's true, then the electric force should cause those protons to just all go, but they have this strong nuclear force which also holds them together. Again, we're not going to talk about this, but just sort of to keep the list complete. And then the other force is the weak nuclear force, and this is relevant for radioactive processes. You don't really need to know what these are, just, in fact, it's really just sort of to make the list complete. You're never going to see it again in this class. All right. Um, there is, just sort of as an aside, we've looked at Newton's laws for millennia, or centuries rather, excuse me, sort of how things move in response to the gravitational field. And from that, we've had this idea of Newtonian dynamics. We can predict where things are going to be based on the forces that are at play. And we know these really well. I mean, that's why we call Newton's laws, because they've been proven over and over and over again. And we not only prove them in the sense of on Earth, like we look at things and as they fall and as they're moving in the Earth's gravitational field and as they move in response to forces, those all represent the acting out of Newton's laws. But we've also seen how these act out on very large scales, right? Have you ever heard of Kepler's laws? Kepler's laws describe how heavenly bodies move around, how they orbit other bodies, and those are all based on Newton's laws too. So the planets and the sun, these all follow Newton's laws. But now there's this new idea coming out, or it's been out probably for a couple of decades, but this modified Newtonian dynamics. And it just says over very large scales, uh, Newtonian dynamics begins to break down. Or it's not so much that it breaks down, but you have these extra terms that come into play over very large scale. You could say maybe like perturbations, if you'll call them like that. These just sort of extra things that slightly change Newton's laws. When I say very large scales, I'm not talking about on the scales of solar systems or even galaxies, but on the scales of the universe, right? When we're looking at big clusters of galaxies or over very, very large distances. So this you can Google this if you want to know more about it, but it's an idea that's taking root, or at least it has over the past few centuries, or past decade or two. All right. So Newton's first law. Actually, let's watch this video first. This is a Veritasium video, and he's just talking here about what are the incorrect laws of motion. We all have ideas about how we think things move, and for the most part, our ideas are incorrect. That we generally don't think about things and the way that they move in a correct way. It's because we have this sort of, well, we'll talk about Aristotle versus Newton. Aristotle had a very different way of thinking about how things move, and Newton, the big breakthrough with Newton and these laws of motion was that he showed that this Aristotelian way of thinking about things is completely false. And we still sort of walk around with this Aristotelian view. And what this guy is going to present is sort of the Aristotelian view of the laws of motion. So let's watch this, and then we'll talk about the laws of motion. All right, so Newton's first law says this. It says that an object moves with constant velocity. Um, unless it's acted upon by a force. This, by the way, is often called the law of inertia. We'll talk about that in a little bit. Now, as I mentioned, Aristotle and Newton had sort of different ways of thinking about motion. Aristotle Aristotle had this idea that an object's natural state, or that every object had this natural state of motion. we might say not natural, but we might say something like a preferred state of motion. But Aristotle would have a more sort of spiritual meaning to it, that every object in the universe sort of has this state that it wants to be in, right? That it sort of belongs in. Not so much that it's a preferred state, but just that it longs to be in that state. And he would say then that every object, this preferred state or this natural state that it has to be in, is to be at rest. And we say that because you look around at things, and most things are at rest, right? The trees are at rest, y'all are at rest most of the time, unless you get up and move around. Most things are at rest. Um, and if you actually read some of his things, he talks about like if you shoot an arrow up into the sky, that it's as if you're creating this really violent event where you're wrenching it from its natural state and putting it into this state of motion. Now, Newton came along and he said, you know, something very different, that there is no preferred state, or there is no natural state, but objects continue in whatever state they're in. So if they're moving, they'll continue moving. If they're stationary, they'll continue to be stationary unless something acts to change that state. So Newton would say if you have an object that's moving, it's going to continue moving forever. It will continue moving forever unless you do something to change the state of that motion. Now you all probably think that you're Newtonian thinkers, right? Because we like to think we're sort of, you know, above the Aristotelian view, above superstition or above whatever. But you'll see later when we answer some questions that you still sort of harbor these very Aristotelian views. They've been ingrained in our head for so long, for thousands of years, that we think in that way. Largely because we still look around and we see things the way that Aristotle saw things. That is, that everything's at rest. Um, but really we want to think in, when we're thinking about things moving, we want to think in terms of these three laws that we'll posit. All right, before we move on, I want to define what a net force is. A net force is just a vector sum of all the forces. All right, so if I have a force that's this direction at 20 newtons, if I have a force in this direction that's 10 newtons, then the net force here is going to be 20 minus 10 are 10 newtons. And then likewise, we can have forces that act on different axes, and then the net force will just be the vector sum. So all that stuff that we did with vectors is really going to come to head in this chapter, largely in this chapter, though we'll see it in other chapters as well. But you'll do a lot of vector addition and stuff here. All right, let's try these little quick test questions. These are from multiple choice questions from old tests. True or false? If an object moves with constant speed, the net force acting on it is equal to 0. Is that a true statement or is that a false statement? All right, just a few more seconds. I'll stop at 30, at 40 seconds. That's all we got here today. 40. All right. Okay, let's see. If an object moves with constant speed, the net force is equal to 0. So an object will continue moving at whatever state it's in unless a force acts upon it. So if this object is moving at a constant speed, that means that it's moving along the same way that it's always been moving. It's not changing its velocity. Does that mean that a force is acting upon it? No? Why not? Right? There is no force acting on it, or rather there is no net force acting on it, because if there was a net force acting upon it, then the velocity would change. So the answer here is A, that is a true statement. If it moves with a constant speed, the net force is equal to 0. We'll see that with Newton's second law as well. So don't sweat it right now. Don't worry, we'll have lots of time to practice this. Um, let's define what inertia is. As I said, Newton's first law is often called the law of inertia. Inertia is the tendency of an object to continue in its original state of motion. Mass is a measure of inertia. So if your mass is bigger, that means that your inertia is bigger. We measure our inertia in terms of mass. If our mass is smaller, that means our inertia is smaller. So that means, for example, if you have a really big block or a really big piece of furniture or whatever, it has a lot of mass, that means it has a lot of inertia. That means that it's going to be very difficult to change its state of motion. So if it's stationary, it's going to be hard to get it moving. If it's moving, it's going to be hard to stop it, right? On the other hand, if you have a really small thing with a small mass, it has a very low amount of inertia, so it's going to be very easy to change its state of motion. All right. So Newton's second law, this is often called the law of acceleration. So we have the law of inertia, the law of acceleration. Uh, Newton actually framed this in terms of momentum, and we'll come back to this a little bit later. I'm going to just sort of write as a little thought bubble. You might not really know what this means right now. But Newton actually said that the force is equal to the change in the momentum as it relates to time. So this was actually the way that he wrote Newton's second law, and we'll see that when we get into chapter 6, when we get into momentum. But usually people describe it in terms of the acceleration. By the way, this is, if you're interested, the momentum is actually the mass times the velocity. So this would be m times dv over dt. And notice that dv dt, that is what? Our definition of dv dt is, that's the acceleration. So that's where we sort of get the standard view of Newton's second law. And he says that the acceleration is directly proportional to the net force, and it's inversely proportional to the mass. So if we put this together, we get A is equal to F over M, or as you usually see it, F is equal to M times A, which is the same as this original form that Newton expressed Newton's second law in, which was in terms of momentum. Again, if you don't know what momentum is, that's fine. We'll get to it. We have a whole chapter on momentum. It's useful for when you're dealing with collisions, and it's actually useful for sort of developing a classical view of thermal collisions. Uh, we can also extend Newton's second law to 3 dimensions. So if F is equal to ma, we can say, and by the way, this is more particularly, it is the sum of the forces. This is the summation sign. So it just means the vector sum of all the forces or the net force. By the way, sometimes I'll say the sum of the forces. This is equivalent to saying the net force. And both of them just mean a vector sum. So we can apply this to the 3 dimensions. That is, we can say that the sum of the forces in the x direction is max. The sum of the forces in the y direction is may. And the sum of the forces in the z direction is maz. That's going to apply on all 3 axes. And this is when we get into applying Newton's second law to static or dynamic situations, is going to be these 3 expressions that we'll use to develop the equations that we'll use to solve whatever the problem is that we're looking at. Equations in this chapter are really simple. We only have 2 equations. We have this one, this F equals ma, and then we'll have another one related to friction. But there are really no new equations. In fact, up till now, you really only have three equations. You have those two kinematics equations, and then you have the F equals ma. So there aren't really that many equations, but as you know, the difficulty isn't in knowing the equations. The difficulty is in actually being able to apply them. Okay? All right, so let's go on. Oh, shoot, I didn't bring that MCAT problem. I'll just make up a problem of my own. It was similar to this. So let's say that we have a rocket, 1,000 kilograms, uh, moves from a speed of, say, 10 meters per second to 30 meters per second in 10 seconds. What force acted on it? Nice, simple, one-dimensional problem. All right, I have a rocket. It's 1,000 kilograms. I have an initial velocity here. I have a final velocity here. And then I have the time. So I know the mass is 1,000. I know the initial velocity is 10. I know the final velocity is 30. And I want to know what is the net force that acted on it. In this case, these are all in the x direction, we'll say. Uh, so I know to find this net force, I have to know the mass, which I know. I have to know the acceleration, which I don't know. But from our basic kinematic stuff, we can figure out that acceleration. I can say v is equal to v naught plus at. V is 30. Let me, I'll just solve this for a. A is v minus v naught over t. That's going to be 30 minus 10 over 10 seconds. So that is 20 over 10, 2 meters per second squared. So if I want to know the force that's acting on this, I just say 1,000 kilograms, that's the mass, times 2 meters per second squared, and that's going to equal 2,000 newtons. 2,000 newtons. I haven't stated this yet. I will in just a bit, and we'll show you the basic SI units. But the units for force are the newton, which is a capital N. By the way, just so you know, did y'all know this? A little bit of grammar for you. If you have a unit that is a proper noun, like a newton, because it's based on the guy's name, when you write out the word like this, you don't capitalize it. When you write out Isaac Newton's name, you'd capitalize that, of course. But when you write out the unit that's based on his name, you don't capitalize it. But when you abbreviate it, you do capitalize it. That's why some abbreviations are capitalized, like the Newton, like the Watt, like the Coulomb, because those are all based on people's names. And some units, like the gram, the second, what else? You get the idea. Those are not based on people's names, so they're not capitalized. A little bit of grammar for Friday morning. You like that? All right. All right. So that's a good basic problem. Sort of get us segue into this. You probably won't see a problem this simple on the test, of course, but we'll work through some that you will see. All right, this one's a little bit more difficult. You have an object that's actually moving, it's accelerating. I want you to try this out. I'm going to sort of highlight the steps. First of all, you want to draw your vectors, draw your forces. All right, in this case, they're all going to be on one axis. How many forces do you have acting on this guy? You have a block and an elevator. The elevator is accelerating downward. How many forces do you have acting on this guy? You just have two, right? So you want to draw those forces and label them. Then you just want to apply Newton's second law. That is that the sum of the forces is equal to the mass times the acceleration. And then you just want to solve for whatever it is that you're looking for. In this case, we're looking for the tension in the rope. So you want to solve for Ft. So draw out your forces first. You already have the picture there. Apply the second law, being careful with your signs, and then solve for the tension. Let's do about 15 more seconds. I'm going to stop at 240. Just guess if you don't know. 10 more seconds. 240. Let's see what we got. Oh, that's not right. Okay, let me show you. So here, first I want to draw my forces. I draw the weight here, and then I have the tension here. All right, so I've drawn the forces. We'll see when we get into 2D forces that we'll have another step where we'll draw what we'll call a free body diagram. But that's not really necessary here because they're all on the y-axis. It's pretty simple. Now I'm going to apply Newton's second law. I say the sum of the forces equals mass times acceleration. How would I express the vector sum of these forces, this Ft and Fw? I say Ft minus Fw. And then that's equal to the mass times the acceleration. Let's see, what is the weight of this object? I think this is where y'all messed up. That was my fault. What's the weight? It's not 10, in fact. I'm sorry, I didn't tell you this. But here, the weight is equal to the mass times the acceleration due to gravity. This is really just Newton's second law. It's F equals ma, right? But I know that my acceleration due to gravity is equal to g, which is negative, or is 10 now. I'm going to let g equal 10 meters per second squared. And so my weight then is 10 kilograms times 10 meters per second squared. So it's going to equal to 100 newtons. Notice, guys, that we have not expressed this as negative 10. We do not express it as negative 10. Instead, we express it as positive 10. Anybody know why that is? I know the acceleration due to gravity is down, so why would I not express that acceleration due to gravity g as being negative 10? That negative is somewhere else. Where is that negative expressed elsewhere in this problem? Brandon, where is that? No, no, that's a good guess, but that's not it. No. This object is accelerating downward, but that's not where the negative in g is expressed. Cody, do you know? Right. So my negative g is expressed right here. Because I draw my Fw acting downward, then that encapsulates that negative. So whenever I'm calculating the weight, I'll use a positive 10, not a negative 10. Whenever you're doing projectile motion problems, you'll take your g to be negative, your acceleration due to gravity to be negative. Usually books will express them differently. When they're talking about g, they'll call it g as positive 10. When they're talking about the acceleration due to gravity, they'll just call it a, or maybe a sub g, and that'll be negative 10. So don't let that I mean that is correct actually. Don't let that skip you up. All right. So now I'm going to put in my values here. I'm looking for Ft. I know that Fw is 100, so I'll take that over. 100 newtons plus mass times acceleration. That's going to be 100 newtons plus the mass of whatever the object is. It's going to be 10 kilograms. And now another sticking point is the acceleration. My acceleration is 2 meters per second squared. But Brandon, you've already said it's down, right? So what's the sign of it? When I was going downward, so negative, right? So my acceleration is negative 2 meters per second squared. And then I just solved this for Ft. It's going to be 100 minus 20. That is 80 newtons. So C was the right answer. See, those of you that put B, I think that this was the problem. Is that right? That you didn't have 100? Yeah, so if you put 10 minus 20, well, once you make that mistake, it's sort of the answer never really pops up, right? Y'all follow me on this? How to work these? This one's pretty simple. You could see one like this in the multiple choice, but we'll get to some more complicated ones today maybe, or maybe next time. Let's try this one. This one's a 2D problem. Here, you have an object that's supported by ropes, and I want to know what is the tension in the rope on the right. So you're going to follow the same procedure here. You'll label all your forces. In this case, how many forces do we have? I have 3 forces, and then you'll draw them onto the figure. I'm going to help you out with this one a little bit. I have 3 forces. I have 1 force here, that's my weight. And then I have FTL, and I have FTR. I want to pick a coordinate system. In this case, I'm going to pick a coordinate system that looks like this. You'll see that yellow, sort of. I'm going to pick a coordinate system like that. Usually the coordinate system that you pick will be obvious. In this case, it's fairly obvious. You want to pick a coordinate system that gets as many of the vectors as possible onto an x or y axis. In this case, just this standard coordinate system will work. All right, so first, label the vectors. We've done that. Second, draw a coordinate system. We didn't do that before because it was just a 1D problem, and it was too simple to really worry about. Draw the coordinate system. My next step will be to resolve the vectors. Notice that I have 2 vectors here that are off axis. I want to resolve those into their x and y coordinates. What do I need to know in order to resolve them into their x and y components? I need to know what? I need to know the angle, right? So I need to know, yeah, this angle right here. I need to know what that angle is. I'm going to redraw this a little bit over here. There's my coordinate system. Here's my FW. Now, what is this angle equal to? It's equal to 50 degrees. In this chapter, you're going to revisit some of your 9th grade geometry, okay? So just I'll draw this figure and show you. If I have 2 parallel lines, I'm drawing this line and this line, and then I have a line that crosses over them like that, then I know that these 2 angles are equal, right? So what I've drawn there is I've drawn this angle, and I've also drawn this angle. You'll get the hang of it. If you've forgotten your geometry, most of the stuff that we're doing will be fairly intuitive. Y'all can see this? You can intuit this, that the angle should be 50 degrees? No? Yes? Okay. Now I want to resolve my vector into its components. The x component is given by what? Cosine or sine? Cosine, right. So I want to find my x component of both vectors. This is going to be FTR cosine of 50. Over here I'll have FTL cosine of 50. And then I have 2 vectors pointing up here. This will be FTL sine of 50, FTR sine of 50. Third step is resolve the vectors. The fourth step, because I have this vector on the right here, it has a y component, and then I also have this vector on the left, it also has a y component. And both of their y components are in the positive y direction. Resolve my vectors, and now I just apply Newton's second law. Once you get to this step, you're basically done. It's just all algebra from here. Though sometimes the algebra can be a little involved. All right, so now we apply Newton's second law. I say, remember, I'm going to have 2 instances of Newton's second law. The sum of the forces in the x is equal to max, and the sum of the forces in the y is equal to may. That'll give me 2 sets of equations, and if I have 2 unknowns, I'll be able to solve for 2 unknowns. This is a particular type of problem. This problem is called a static problem. In a static problem, the acceleration is equal to 0. those of you that are engineering, you'll have a whole semester of just static problems. We'll get more into that later in the semester when we get to equilibrium. That'll be more like the problems that you'll encounter in your engineering class. But this chapter especially sort of forms the basis for a whole year of classes that you'll take in statics and dynamics. They'll be a little more difficult, of course, because you'll spend a whole semester on it. There's a whole sort of range of problems that you can look at. But and then for some of you engineering students, like this will be your bread and butter for your whole life. You'll work a lot with sort of forces and equilibrium forces a lot as you build structures and what have you. Okay? All right, so this is a special case where a is equal to 0. So both of these terms go to 0. Makes the problem quite a bit easier. And then I just write up my equations. So in the x direction, I have ftr cosine theta minus ftl cosine theta, or cosine 50 if you want to write it that way. I'm just going to keep theta. That's equal to 0. From this equation, I can tell what? I can tell how these two forces are related. Which one's bigger, FTR or FTL? They're going to be equal, right? Because if I write them, FTR cosine theta equals FTL cosine theta. Notice that my cosine thetas cancel, just telling me that FTR is equal to FTL. So from here on out, I'm just going to call these FT because the right and the left are identical. This problem's made really easy because the angle theta are the same, that they're both at 50 degrees. But in your homework, you have a problem where you have ropes that are set up so that the angle is not equal, something like that. And you'll see that that problem is a lot harder because these angles don't cancel out. And you have to actually solve a system of equations because the FTL and the FTR are going to be different. I'll leave that. We'll work through some problems that are similar, but you should take a look at that problem in your homework as well. Maybe even this weekend, take a look at it. All right, so I'm just going to call these both FT, and then I can go over to my some of the forces in the y direction. I have FT sine of 50. Look, since I know they're equal, I'm just going to multiply them by 2, because FT sine 50 plus FT sine 50 is just 2 FT sine 50 minus FW, and that's equal to 0. I'll leave you there to finish that up, okay? And go ahead and click in your answer. Although basically the answer is done now. You just have to solve this equation for FT. All right, folks, let's try to wrap it up, okay? Just solving this equation for FT, and that'll give you your answer. All right, we'll just do about 10 or 15 more seconds. Just guess if you're not sure. Like most of you have it right so far. We'll stop at 9:38. 9:38. Okay, awesome. A is the right answer. uh, I say Ft is equal to Fw over 2 sine 50. Fw is 230. That's the 23 kilograms times 10 over 2 sine 50, and that's equal to 150 newtons. So that's the right answer, A. All right, folks, that's a good example of a 2D problem, though still a little simpler than what you would see in the free response. You might see one like this. I could give you like one like this that would be pretty easy, and then a more difficult one. But you should certainly be able to work forces in 2 dimensions. Don't worry, we're going to see several more examples, and you have some in your homework as well. So I know probably a third to 2/3 of you still are not getting it. Is that right? Yeah, not getting it. But we're going to have lots more practice with it. Um, Go down from here, y'all. Okay. Now let's step back. Just want to review sort of the process here. Remember, we draw our forces. Each problem you have will have the same procedure, but each one is also a little bit different, right? So they're kind of like getting a puzzle and trying to figure out how to undo the puzzle. But you follow the same procedure each time. You draw the forces. Uh, you will draw also a free body. Oh, I'm sorry, this is the wrong figure. You draw the forces, you draw your coordinate system. This is also called a free body diagram sometimes. A free body diagram is just this thing. When we draw all the forces that are acting on a particular object, you resolve the vectors, and then you apply Newton's second law. And then from that, it's just algebra. It's given, I got 2 or 3 equations. How can I solve this set of equations? That in itself is a useful skill that you'll use a lot in your coursework from here on out. But applying second law, right, using that sum of the forces is equal to the mass times the acceleration, and then solving them. In this case, it was made a lot easier because, first of all, we had 0 acceleration in both cases, so it was a static problem, and so that acceleration term just went away, which made the solution a lot easier. It was also made a lot easier because these cosine theta terms went away. If those didn't go away, then FTL and FTR would be different variables, and we would not be able to say that they were just FT. And then we would have FTL and FTR, 2 separate variables with 2 separate equations, and we'd have to solve a system of equations. Okay? All right. Let's do another. Let's see. Let's look at the units. As I said, the unit of force is the Newton. Um, I like to sometimes give you problems in the multiple choice, just asking about the basic SI units. 1 Newton is a basic SI unit of 1 kilogram meter per second squared. If you get that question, don't freak out. Just remember the equation where that unit came from. So for example, F is equal to M times A. M is kilograms, A is meters per second squared. So that's where that comes from. We're going to be building units on units a lot as we proceed from here. So this is sort of our first time to build a unit on those MKS units, the meters, kilograms, and seconds. We'll see this again with energy when we do joules. That'll be based on basic SI units, work, uh, momentum, on into next semester when we do forces and fields and all sorts of stuff. What's the unit for force in the United States? We use the British system. I know. No, a foot-pound is either a torque, yeah, that's a torque, but a torque is a force times a unit length. So in the British system, our unit for force then, not a foot-pound, but just the pound, right? So the unit for force in the United States is the pound. So it would be akin to a newton. In fact, what a newton, I think, is about a quarter pound or so. Um, Person weighs about 700 newtons. That's about my weight in newtons. A small apple is about 1 newton, about a quarter pound. And by the way, do you know what the British unit for mass is? Right, in the metric system, we have kilograms, which is mass, but then we convert that into a force depending upon the acceleration due to gravity. And so we usually talk about our weight in newtons. But in the British system, what is the unit for mass? This is just really cool. Do you know, Zane? No, it's not a stone. I don't know what that is a unit for mass, but I don't think that's in the British system. Are you confident in that? Okay, I'll have to look. I'm pretty sure that that's not the standard. I'll look it up though, Cody. I could be wrong. I'm not gonna test you on it, but it's the slug. I'm pretty sure, or it might be the stone. But either one is cool, right? Because I'm pretty sure it's a slug. All right, that's just a little trivia. Let's try this quick test. Is this statement true or false? It is possible to have motion without a force. That is, an object can be in motion without forces acting upon it. Okay, 35, I'll stop. That is true, right? Newton's first law. Uh, if an object isn't moving, then no force acts upon it. Is that a necessarily true or is it necessarily true or a false statement? If an object isn't moving, a stationary object has no forces acting upon it. Stop at 30. He is right. Very good. Hey, what did the fish say when it ran into the concrete wall? Damn. You heard that one before. Okay. Hey, right. Yeah. All right. So you're stationary, right? But you got a whole heck of a lot of forces acting upon you. You got a force weight. You have another force that's pushing up on you from your chair, and then within your body, you have all sorts of intermolecular forces. Your muscles are acting on. There are all sorts of forces. But you know, you sitting in that chair, you have the sum of all those forces is equal to zero because you're stationary. So if an object isn't moving, that doesn't mean that no force acts upon it. It means if I wanted to make this a true statement, I would say no net force acts upon it, right? That the sum of all the forces is equal to zero. Listen, folks, the next few class periods before that exam, we're going to be working some problems that'll be a lot like the ones that you'll have on your exam. So make sure that you come, but also be working that homework, the homework problems. They'll help you with the coming up on the exam. Students often find these things kind of difficult to work these Newton laws problems, but they're important. Well, they're important for all of you, especially for the engineering students, but they're important for all of you. All right, you all have a great weekend. I'll see you on Monday. Remember, it's a short week next week. We just have Monday and Wednesday class next week. Fall break. Fall break number one. We have two fall breaks this year. Did y'all know that?